All right, let's continue. Last thing, ML-based classifier. That's what we're going to use a lot. ML, we're going to use supervised learning. So we wouldn't require label text data, but that's the paradigm that gives you the best result. So some popular models that we use now is logistic regression and a lot of deep learning models. All right. So today we'll talk about none of them. We'll talk about naive-based classifier, but quite quickly, just so that you get the idea of how to think about classification. So supervised learning has 4 steps. First, we'll talk about each step. First, data preparation. Data preparation, I think about it as a task formulation. So what the input and the output should be. Since you've got to train the model, right? So the model, you have to train the model. So the data that you prepare should match how you're going to use it. So that's a very important consideration. So if you want to use it for, say, for sentiment on Pantip, for example, which is a web forum, it's going to have different language to it, right? And also different length, different topic that we'll talk about. If you draw it from X, then it's going to be different length, different language as well. So you have to choose the data sources that you want to use the classifier for. So the more you can make it match your data source, the better. Okay, because sometimes you don't have everything. you have what you have. And then you have to define what you want to classify. For example, if you want to do sentiment, you can do it at the sentence level. You can do it at the document level, or you can do it at the document, at the whole document level. I just said that. Sorry, sentence level, paragraph level, or document level. So you have to choose what kind of thing that you want to classify. Okay, and then you have to define labels. So these should be the labels that are useful for you. For example, if you do sentiment analysis, you could do positive, neutral, negative, which is great, but then it's a bit harder to make a data for because it's 3 labels instead of 2. Sometimes you want it to have 5 labels: strongly positive, positive, neutral, negative, strongly negative, for example. So whatever your applications are, then you need to choose the right labels for it. Okay. Next, data annotation. Sometimes you get to hire somebody to do it. Usually you would actually when you work as an AI engineer and NLP engineer somewhere, and if you want the training data, so usually you can get those. And so data needs to be labeled by humans usually, and it's kind of slow. Fortunately enough, with good NLP models we have now, we don't need that much data. We need like 1,000, 2,000, something in that order, not tens of thousands anymore. Okay, so that's the good news. But yeah, data annotation, it's its own monster because some tasks are easy to annotate. Some tasks are not very easy to annotate. All right, that's all. I'm going to talk about data preparation. Next, we'll talk about that's something that make a basis for your model is feature engineering. What is feature engineering? Because in vision, for example, what's a feature? A feature is basically each pixel, because that's a very good feature. Feature is something that the model should pay attention to. It's something that can help you predict the label, okay? And in NLP, we need to do feature engineering because your text is just string, okay? So you want the meaning, right? The meaning actually indicate the label, usually. That's what we want to get to. But strings are not meaning. Words are meaning, sort of, but words in the sentence will indicate a stronger signal for for the meaning, right? So that's why feature engineering is quite complicated for NLP. So yeah, I just said that. So making making a feature vector is called feature engineering. So if you have a piece of text, you have to turn it into numbers. Okay, so each one document could be 013, the other one might be -104, 103, 114. So that's what we're going to work with. We're going to throw the string away because strings are not meaning. So we want to extract something that keep the meaning of the string, and that's what NLP models are all about because language is hard. Okay, and we call this thing a feature vector. A vector, as in what you learn in linear algebra, is a vector. So it has a magnitude, it has a direction. So that's the model, okay, that we're going to use. We use a vector space model for machine learning. How do you get a good feature vector? That's what we'll talk about very extensively. Oh yeah, feature vector. So one feature vector that we use a lot is called back of word feature vector. So for example, if you have a text like this, which is a movie review, right? So how do we turn it into a vector? How we do it is that we use a back of word, as in we shake it. We put it in the bag and shake it, because then it loses all the word ordering. You can't reconstruct the original text anymore. So which means the model will know nothing about original text or word ordering. It just knows how many words appear, which word appears in the document. And to turn this back of word into a feature vector, so you indicate the vocabulary that you want to include in your count, and then you count how many times each word appear in the document. So in this example, it appears 6 times, I appear 5 times, they appear 4 times, and so on. And you do that for all the words in your vocabulary. Okay, so your vocabulary, once again, can be 10,000 words, 20,000 words, up to you to specify. And then you have a vector, right? This is a vector now. See, it's a bunch of numbers put together into a column thingy. So that's a vector, right? So now you have a feature vector, which we will compute with later, because with numbers you can compute. With string you cannot compute anything. So NLP is about turning text into a bunch of numbers so that we can do useful things using models. All right. So yeah, back of word features, we'll see another example today. And the third step, once we know how to turn each text instance into a feature vector, we will train the model now. And once this feature engineering step is done, model training is not very hard. So we feed the training data, which will turn into whatever feature vectors that we have designed. And then the model will learn from the pair of feature vector and the label. Okay, we'll learn how those numbers relate to the label. Okay. To do that, when we have the data, we will always split it into 3 sets: the training set, validation set, and test set. All right. So once we have the data set, say like 10,000 instances or 10,000 rows, 10,000 records, you can use one of the words: rows, records, instances. All right. We'll split it into 3 parts, 3 chunks, 3 sets. Training set is actually for training. That's what the model will study from directly. And we have validation set, which is for evaluated, so that you know how good it is. And test set is like a final exam. You should never look at it. You should use that once. Okay? So for example, we will split it something like that: 60, 20, 20, 8, 10, 10, 70, 15, 15. There's no real answer to how you should do it. But training set should be the largest, because then it can have the chance to perform well, right? Because the more samples it gets, the better. That's the rule. And validation set and test set should be large enough that you can see whether they perform well or not. Like, think about if you take an exam of sort and it has 10 questions versus if it has 50 questions. The test with 50 questions is usually better, because then you get to test the student on many things, right? So you have a bigger picture. But if you have too few questions, as in your test set is too small, then it's not very good at assessing the performance. Okay, so we usually, when we have the data set, we split it into these 3 sets. Or if you download it from online, they already split it for you, so that everyone uses the same test set, so that you know how well you do compared to other systems that come before you. But in real work setting, you get your own data. You might have 500 rows, and you split your own, so you can do anything you want. Okay. With some limitation. So when you prepare the data, if the data is ordered by date, then you don't shuffle it. Usually you shuffle it so that test set and training set are the same distribution. They are not too far apart, so that whether for sure whether your model performs well or not in general on average. But sometimes you don't want to shuffle it, which is a lot of the time. So for example, if you shuffle it, then you see that the date for the data, for example, if you don't shuffle it, then it's going to look like this. So many times you do this actually, because then you simulate the future. So the test set represents what you haven't seen. I don't know, when 2 days later, from January 8th to January 9th, something might have changed already. So if your data have time stamped to it, sometimes they don't shuffle it. But a lot of the times, if the time doesn't matter, then you shuffle the data first. Okay, so they well mixed up. Yeah, shuffle like this. Oh yeah, deduplication. Okay, deduplication, that means duplicates means things that repeat. Deduplication means you remove things that are the same in the data set. This can happen a lot, actually. So we don't want this, because if your say the text that you get in the training set and the text that you get in the test set are exactly the same, it's not a good test set already, because you have seen that text already. Okay, so you want to deduplicate, because sometimes that actually matters. Okay, especially in short text, right? Sometimes people say the same thing over and over, but different people. So it can give you a false impression that your data is good and your model is good. It's good because it has seen that data before. All right. Now we can train the model. To train the model, each model has its own formula, different equation on how it uses the model. It uses the data. Okay. Once we train the model, we evaluate on the Dept set. Oh, sorry. The validation set has 2 more nicknames: holdout set and Dept set. But they're all the same, okay? It just depends on who prefers what. But I like Dept set because it's short, because I don't say development set, I say Dept set. But if you say holdout set, validation set, it's good too. Sometimes they just make it val dash set, val as in validation. So you might see that as well. Okay, but these are the same thing. So, yeah. Oh yeah, okay. Once you evaluate it, has only train parameter. So once you train the model, you always have to evaluate it on the depth set, okay? So that you know how well it does. Okay, so evaluation, super important because we want to know, whether there's a bug in your code or not, okay? So if you train the model and you think, oh, it's already trained, you like put it on production and you never test it basically. So if you test it on the dev set, then you know whether, oh, you get 60% accuracy, I'm doing something right. If you get 5% accuracy, you know there might be a bug in your code, for example. Okay, so this is a very good way of developing a model. Yes. Let's look at a model. We look at this first model, naive-Bayes model. We don't use it much anymore, but we will talk about it briefly so that we know how model training works, because other models, you don't see it anymore. You just throw it in there and it will just train, okay? So I want you to see it once on how the model is trained. Okay, so naive-Bayes classifier, all right? It uses Bayes. It uses Bayesian inference. It's from probability theory. You might have seen it. If you haven't seen it, it's fine. Here's how it works, okay? It uses probability, okay? So you have two variables, x and y. Y is a label, x is the text data, okay? So you want to create this model. It's a probabilistic model. A P of y is positive given, we will say given that, or it means you already know that, okay? That's what this bar means. It means people read it as given or assuming that you know that, okay? Assuming that you know that the text is predictable but very fun, okay? So translate that into English. It means you ask a question, if the text is predictable but very fun, okay? What is the probability that the label is positive? So you want to have to train the model to answer this question, okay? So it would not give you just the label if you give you a probability, which is great because then you know whether you are confident or not, right? So if you observe the text and the probability is 50-50, between label positive and label negative, then you know that you're not very confident. So probability is great, okay? So naive-Bayes model has its own way of computing this probability, okay? And each model has its own way as well, but we always use probability here. Okay, and for negative as well, we ask the same question using this notation. All right, here's some formula. We cannot be scared of formula, all right? So this is called Bayes rule, Bayesian inference. There's a formula to it. Okay, just think about it as a formula. Then you flip this x and y to x given y, and y is positive. So you have two more terms. Let's look at the denominator, the downstairs. So the downstairs, you notice that it's kind of the same as upstairs, right? But you also sum it with when y is negative as well. Okay, you see that this term upstairs and the first term in the downstairs is the same. All right. Okay, so P of x given y, this is called likelihood of the data, okay? It's called likelihood, we will use it a lot. So then you ask this question and you compute this from the data. If you know already that the label is positive, okay? If you know already, which you have the data, right? So you know, which means you will only look at the document that are positive. Okay, so looking at only the documents that are positive, what's the probability of seeing this string? Predictable, but very fun, sorry. But very fun. Sorry. Change that. Okay. So then we need a model to compute this probability. Okay, this is our language model. And the other term, P of y equal to positive, this is called prior probability. So it means if you don't know the text at all, what's the probability of positive label? So we look at the data and see how many times we see the positive label. So we do the same for negative as well. And again, I want you to see this pattern from this formula. For positive, you can see that this whole term is in the denominator as well, right? And for the negative, it's also in the denominator as well. Okay? So which means on the downstairs, it's the same for both labels. So I'm gonna substitute that with z, okay? Which we'll compute later, because once we compute this, and we compute this, then we can compute z, because then we sum this term and this term together. Okay, so it's some formula. Awesome. Good, 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 good. So how do we compute this guy? Okay, this guy, P of x equal to predictable but very fun. Then we decompose it into each token in that string, and we multiply them together. What's the probability of seeing this word, given that you know that the document is positive? Should be pretty low, right? If you think about it, predictable is not a very good word for a positive document. But also it could be, it should be 50-50 if you don't know that, right? But look at this one. The probability of seeing the word fun given that you know it's a positive document. If you only read positive documents, what's the chance that you see the word fun? Pretty high, right? It should be quite high. So this will set this apart from negative label. Okay, this will contrast. Let's look at how we compute that actually. I have the link on here, and I have some example on how to actually compute these things. Let me zoom in a little more. Okay, so first this is your training data. Okay, this is your training data. So you have 3 negative labels and you have 2 positive labels. Okay, so suppose you have 1, 2, 3, 4, 5. You've got 5. You've got 5 instances in your training set, and you construct back-upward feature. Suppose you will only look at these, how many? 11 words. In practice, there'll be a whole lot more. Okay, but we will look at these 11 words only. These are your vocabulary. Okay, that's when I say, oh, you need a vocabulary, this is it. But we make a simple model now, only 11 words in the vocab. And if texts are predictable and boring, then you have this feature vector. Okay, 1, 1, 1, 0, 0, 0, 0, 0 until the end. Very few laughs. And then your feature vector looks like this, 0, 0, 0, 1, 1, 1, 0, 0, 0. So a lot of them would be 0. Okay, because if your text have 100 words and your vocab is 30,000, then you have 20,000 something zeros, a lot. Okay, so that's bad. Actually, that's quite bad. Yeah, short and boring. Again, you have a feature vector that looks like this. So hope it's this is more concrete now, what I mean by a feature vector, okay? So yes, this is feature engineering. So you use what vocab you want to include in your count, okay? Again, in practice, you write a for loop over the tokens that you tokenize. We know how to tokenize now. Now then we know how to count the words that occur in the text and turn it into a feature vector like this. So from this string to this vector should be pretty easy. You write some code, all right? Again, very powerful, blah, 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 okay? So if you see words that are not in the vocabulary, so it would not show up in your feature vector at all. Okay, so that's why you have to know how many words and what words you want to include in your vocabulary. Awesome. Okay, so it will look something like this. Let's go back to the slide. And so next concept is model parameter. So every model would have a parameter. So what a parameter is the numbers that the model would use to predict the label for you. And these model parameters are learned from the data. Okay? Any model that we see from now on, I'll use this word parameter. And we are in supervised learning. We will learn the parameters from the data. Okay? So for naive Bayes model, you only have to count and plug it into the formula. It's not very hard. So first, you have to estimate the prior probability because it's one of the labels or one of the parameters. These are all the parameters that you're going to train, okay? So you have prior probability for each label. And also, the probability of each word in the vocabulary for that label. And again, the probability of each word for each word for that label. So these are model parameters, okay? Which I think already plugged in the right formula for it, yeah. But I'll show you the formula first. So first, prior probability. Prior probability, we need prior probability of negative example and the positive example. So for this one, this is the same data set. So the prior probability of positive is the number of documents that are positive divided by all documents in the training set. So if you don't know anything, right? If you don't know anything about the data, what's the chance of getting positive label? It's 3/5. Okay, it's 3/5. So far so good. No, it's 2/5. I'm sorry. 2 because there are 2. I'll upload the new slide. Okay, it's 2/5. Okay, so positive. So got 2 here out of 5, right? You know basic probability. You know it from high school. Okay, next model parameter that we need to train is this. How many times would you expect? What's the probability of seeing the word predictable? Given that you only look at negative document only, and the same, what's the probability of seeing predictable? Given that you're looking at the positive documents only. All right, that's not so bad, right? Predictable, so we'll look at positive only. Positive only, so it's 0. Okay, so yeah, so it's 0, and that's fine. That's great. So if you look at this one, predictable, negative. How many times you see that it's 1 out of all of the words that you see, right? So yes, something like that, okay? So yeah, there's some formula, okay? And then you compute each parameter based on the formula. I don't expect you to know the formula, by the way. I just want to give you one model where we can train the model just in Excel spreadsheet, in Google Sheets. So there's some formula, there's a few variations, but I'm just gonna talk about it this much, okay? Because it's not that important anymore. All right, so I hope from this you understand what? You understand that you have to create a feature vector, and each model has a model parameters. And when you learn when you train the model, you adjust these model parameters based on your training data. Okay, but don't worry about the specific. That's why I keep going a bit fast. All right, just so that you know these concepts. Okay, so here comes the inference time. So suppose I already trained the model for you, it looks something like this, okay? So when you want to use it, say when you have a new sentence that said predictable but very fun and powerful. When you run the inference, same idea. You turn the text into a feature vector, which is this thing, right? Why? Because predictable appear once, but appear once, very appear once, and so on, okay? So you turn it into a feature vector. Once you have a feature vector, then you could compute the probability based on the equation of that model. Okay, so the equation for this model is actually pretty straightforward. So you for the feature that is 1, you use the parameter from that word, okay? And then once you copy down the parameter for each label, then you multiply it. Something like that. Again, don't worry about the formula. So this is how you use the parameters, okay? So once you have the trained model, you use the model parameters to infer the probability of each label. Okay, and the label with the higher probability wins, and then you then you can classify that text as that label. In this case, it's positive. All right. So that's the first model, which we will never use. Okay, but I want to demonstrate the whole concept of machine learning for NLP. All right. Again, the best classifier we have so far, it has high accuracy when we have a good amount of data. It's very good with noise, actually, because it would know which word or which pattern in the word is a good feature. And even some patterns that you haven't seen before, even for naive Bayes, you will find some words that you did not think indicate positive or negative labels. Okay, so that's the strength of it, because you use the data to inform your model. You don't think about everything about that problem yourself. Cons is that you need the data set, which sometimes you have, sometimes you don't. Sometimes you have to spend a lot of time and money to get it. All right. Last thing that we'll talk about today, though, is evaluation, because I know you know something about model training already. Evaluation in NLP is it's like a tradition. You have to do it because then you are sure you know a little bit more about your model, how well it works. Because usually, all you get back from training the model is what? you get the model parameters, which you will never look at, right? Because it's just a bunch of numbers. You cannot make sense of it. Evaluation make you understand your model, what it's good at, whether it's ready for production, or it needs more data set, more training set. All right, cool. We have a few metrics that we compute based on classification tasks. Suppose we're doing spam classification. Okay, so there are 3 labels. Normal email, it's an ad, it's a junk mail. Okay, so suppose you train a model already and you run it on your def set, and your def set has 100 instances. All right, so you have something called gold standard. So it's the actual label in your def set. We call it gold standard. Okay, not golden, gold, as in it's standard that we can rely on. Okay, it's a gold standard, and you compare it against the prediction. So that's what the system gives you. Okay, and suppose you have 100 of that, and suppose you have this really good system where it doesn't classify it as spam ever. It gives it okay to all of it. So the first metric that we all know is accuracy. Accuracy is like test score. So how many times you get it correct divided by the number of questions, right? So your system is awesome. Got 93%. You can pack up, go home, right? Awesome. It's not. Why is it not awesome? Yeah, it doesn't do anything. We don't have to train anything now. I can just return okay, right? The function with one line. That's not great. So which means this metric is not great for evaluating the system, right? Because it gives you a high score, although we know intuitively that it sucks. Okay, that's bad. Compared to another system that's, it tries, right? But it got some wrong, right? So it got, what's J again? J is drunk, so drunk as ad, okay? So it misclassified that, these can be quite similar, so and it misclassified some normal email as ads, because these can be quite similar as well, right? So what's the accuracy of the second system? 93. Which one do we prefer, A or B? B, because it tries, right? It tries to do something, right? We know that it tries to do something intelligent, right? I'm like, oh yeah, the junk mail, it got, from 4, you get, you get that right? And you never confuse the normal email with the junk mail ever, but you confuse okay email with ads, which is understandable. So we know intuitively that B is better. So the metric is bad, but accuracy is okay for some cases. It gives you an overall idea, right? But in this case, it falls short, right? So we have 2 more metrics that we use religiously. Okay, it's precision and recall. So precision and recall, we will compute for each label. So if we have 3 labels, A, B, and C, we compute precision of A, precision of B, precision of C. So we compute it per label, all right? Here's a formula. Precision is a recall and precision on the numerator, on the upstairs, on the numerator, is the same, right? The number of times that you get that label correctly, okay? But the denominator is different. What should you divide it by, right? For all true A's, or all predicted A's. So it turns out it tells you different things. So for precision, of all predicted A's, how many of them is actually correct? So it tells you if a system says it's A, can you trust it? What's the probability that it's actually correct when it gives you that label? For recall though, you want to know if you have 10 A's, how many of what's the chance of them getting caught? It might be, so let me, this is a formula. Let's talk about the intuition of it first, and I'll go back to the formula. The formula is very easy. Every time, in the midterm, I make you calculate precision recall. Everyone got it right. So I feel like you can see the formula, you can plug in the number, it's not very hard, okay? We will come back to this later. Let me tell you more about precision and recall. So precision is about how much you can trust the answer. If they say it's an A, can you trust that? Okay? But for recall, as in you call it back, right? So how many A's are detected? Let me give you a more concrete example, okay? So suppose you build a classifier to detect plagiarism. You guys know what plagiarism is, right? When you copy other people's work without giving them credit. Okay, there's a system for that. Chula uses that actually. When you write your senior project or something, they will run this plagiarism detection, which is great. So suppose precision of plagiarism is 0.3. 0.3, okay? That means when it said when it flagged, oh, this thing is plagiarized, there's only 30% chance. So probably a 0.3, that is actually plagiarism. So which means some people will be wrongly accused of plagiarism, right? Not great. Also not great, right? Recall, suppose the recall is 0.8. That means 80% of the actual plagiarized thesis will be caught. So 20% of the not cheating, that's too much. 20% of not so, 20% of the bad thesis, let's say, 20% of the bad thesis will not be caught, and they'll get the degree, and they'll walk free. Okay? So A is when like, hey, maybe we can't trust this very much if they flag it as plagiarized, but we know that we'll catch a lot of plagiarism. Okay? So this is the kind of system you get if you look at the number and it looks like this. Okay? Obviously bad. Right? So like you want to be able to trust it, so high precision, right? But you also want to catch more plagiarism if possible. So in a perfect world, super high accuracy system will have high precision, high recall, but sometimes we cannot have both. Usually, if one is high, the other is low. Okay. So if we go back to the formula, okay, back to this picture. So this compute precision and recall. Okay. So for the first system, it said okay all the time. Okay. Okay all the time. So you can only trust it that it's actually an okay email. It's 93%, which is awesome. And recall is 100% because when it's okay email, it's always flagged correctly. And that's awesome. But precision though, this will divide by 0 because it has to divide by how many times the system gives you J, which is 0. So you know that the system is bad. So you get this number and you know instantly by math that, oh, this system never give you junk mail. This system never give you ad, and that's bad, okay? So you don't have to look at this at all. And when you train the model, if you give you these metrics, okay, you give you a precision and recall of each label, and you should be able to read it. All right. So, you see that precision and recall are kind of, we want both. So how do we see the big picture of that label though? We have this extra metric called F1 score. F1 score, they call it a geometric mean. So it's like computing a mean, it's like computing average, but not an average. It has this formula, okay, which I have been doing NLP for like almost 20 years. I look up the formula every time. So it's okay if you don't know the formula, you can always look it up. It's kind of weird. It's like 2 times P times R divided by P plus R, kind of thing. All right, so basically it's an average, a very fancy average. So you get the big picture of precision and recall, all right? So I plug in the formula, that's what I got. But look at the second system though. Look at the precision of junk mail for the second system, right? So it said junk 3 times, is correct 3 times. So the precision is 1, so that's great, actually. But for recall though, we look at how many times that you actually have junk mail. 4. How many times do you catch them correctly? 3 out of 4, right? So that's how you get 3 out of 4. So it differs by the denominator, okay? Denominator, such a hard word to say. Denominator means the number downstairs, okay? And for ads, you can see that it's weak on that one because if you look at the result right here, you see that it gives out too many of this label wrongly as well, right? So the precision is so low because it gives out ad how many times? 10 times, and out of those 10 times, you are correct only 3 times. So it's not very precise, When you give out 10, only 3 of them are correct. So you cannot really trust this label when it says ad. You have to be like, it's only 0.3 probability that it's actually ad, okay? But recall is awesome because add, all 3 ads in the Dept set, you caught them all, right? So the recall is 1. Okay. So we know that if there are ads, we will catch it. You know why? Because it flags a lot of things as ad. So there's more chance that it's gonna catch the real ads. Okay, so it's kind of cheat a little bit, all right? But yeah, and then you can compute F1. And from F1, you kind of know almost exactly that, that your system is good at detecting junk mail, but detecting ads, meh, right? Not that great. Then you need more data, you need to train the model more, you need to change the model, what have you, okay? So that's how you really get to know your model performance because then you can have other aspects of it. Usually you don't compute this by hand at all. There's a function that compute all of these for you. You might have 40, 30 labels and we will compute precision the F1 if recall for all of them for you. But it won't read it for you, okay? So that's why I'm teaching you to read it. Cool, so we can compare these now, and you know that this is not great because if you average, you cannot even take average of this, right? Because this is NA, it's divided by 0, it's undefined, right? Is it undefined or infinity? One or two. But yeah, for us, we don't care because it's some number that we don't want to see, okay? Cool. All right, what about this one? Again, we retrain the model, we have more data, and then we run the evaluation. The precision is 0.9. The recall is 0.4. Is it good now? So if we flag something as plagiarism, we are confident now, right? That it's 90% chance that this one, that thing that is flagged is actually plagiarized thesis. So if you are a professor, you are more confident now. Hey, there's a 90% chance that your thesis is plagiarized. Can we talk? Compared to this system, right? You're like, maybe we would not do anything, right? So how you use the system is very different now. So it's because this is high recall, right? But this is high precision, low recall. So which means if the system really flag it, right? You should do something because you leave a lot of actual bad thesis go, right? Because you don't flag it. You only flag it correctly, those just 0.4, right? So this system is probably better because you can actually do something and you would not, hurt student feeling like, I wrote this myself, why do you approach me with this, right? So in some cases, you want high precision and low recall. So for example, this one, because if you make a wrong decision, then, then your student would not like you. Okay? And we don't want to hurt anyone's feeling. What about this? High precision, high recall. Everyone's happy, right? So bad thesis got caught, and when somebody got caught, you know with a high probability that you're quite confident that it's actually a plagiarized thesis, for example. Okay, so this is the kind of classifier that we want, but we don't always get it. Sometimes you have to choose one or the other. We can always change the models to prefer precision or to prefer recall. All right. Now I'm gonna ask you, before we all go, okay? You build a classifier, okay? I'm a very sensitive man, when they read course eval, when there's bad comment, I'm like, oh, let me get a strong drink after this. It's quite it could be quite hurtful. Okay, so some comments are quite toxic, not just in course eval. So you want to build a classifier, okay, that classify comment as toxic or productive. Okay, so you want to screen out the toxic ones, for example. Usually I use the TA as a classifier, as a TA. Can you go look at course eval and just, talk about the ones that make sense? The ones that are not just like, I hate this professor, which I got sometimes. All right, okay, back to this. So suppose you build a classifier to tag toxic comment, okay, hateful toxic comment. So, and once you have the system on, say, my course field, the instructors won't see the comment at all. Ooh, great feature, right? And you suppose I train the classifier and it looks like this. Precision 0.2, recalls 0.9. What do you think? Do we like the system? It's not accurate, obviously, but can we use this? Depends. Okay, depends on what? Yes, depends.
Whether we actually want to prioritize precision.
Okay. Okay.
Other case,
Okay. Should we prioritize? What should we prioritize in this use case?
well, we want to catch as much toxic content as possible.
That would be great, right? Okay. Okay. Anyone else? Should we prefer recall in some In what case should we prefer recall? I mean precision, yeah.
I feel like I'll go for recall.
Then this one is called.
You will look for the recall. Why?
Because like I feel like everyone will, I mean majority of people will always have some kind of dissatisfaction
Okay.
with the professor.
Okay.
So if it's even a bit of toxic, they will flag it and will comment it out.
Mm-hmm.
So instead of that, the most toxic one would only get commented out.
Okay. So right. So yeah, you're both right. So if you prioritize recall, which this model does, right? Which means the instructor would not see toxic comments almost at all, right? Because around 10% of the toxic comments will get through and they will see it. That's probably fine, maybe, right? But then on the flip side though, if the precision is this low, which means what? A lot, yeah. So when it gets flagged as toxic, you're not sure whether it's toxic or not, right? So which means you screen out a lot of comments, right? Because it will try so hard to make sure they catch all the toxic ones. So you lose some normal comments as well. Okay, so yeah, so I hope that help you understand this metrics is quite. It's quite difficult. So if you prioritize precision, which means you might want to talk to that student specifically, right? So you want to be able to I catch the toxic one. Now I want to look at those more, which might not be the point of this system. Okay. We will talk about confusion matrix next time. So I hope you understand precision and recall now. And at the end, when we do evaluation, when we will put it in a table like this, and then we average over precision, average over recall, average over F1, and we get usually one single number. When we want to compare models, instead of using accuracy, we use the macro average F1, which means you compute the F1 for each label and then you average them. That's usually what we go for because having one number is nice so that you can actually easily compare models.
But that sort of doesn't really tell us anything.
Say again.
It sort of doesn't really tell us anything because again, if we take the toxic comment as an example, if we don't want to see toxic comments at all,
Yes.
we would want to focus on
Recall. That's right.
But then if we're not that serious and we want to get more constructive comments as well, maybe precision.
That's right. Yeah, exactly. Yes, exactly. Yeah. Okay. So yeah, that's evaluation. So if you compute macro F1 for this guy, then it's gonna turn into what? 0.32, right? Which is much lower than 0.75. So now we have a better metric than accuracy. All right, so for all classification tasks, you're going to end with this for all models that you train so that you can compare them. You understand them better, in what way they work well, in what way they work poorly, okay, based on the label. Okay, I think that I'll finish up with confusion matrix. Monday, wow. In 3 days, we'll see each other again. That's exciting. So have a good weekend and no homework, no assignment for today. And for the activity today, don't forget to, put whatever output that you have on my Crossville so that I know you're here.